We studied about the center of mass yesterday, and we know that if we have some body like this, okay, and this body has a number of particles, then how do we find its center of mass? So the position vector of center of mass is given by m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar divided by m1 plus m2 plus so on and so forth up to plus mn, right? This is how we find out the center of mass of the body. Okay, and we saw the significance of center of mass also. So what is center of mass? Center of mass, the definition of center of mass is it's the point at which the total mass of the body is supposed to be concentrated. Okay, so this is the position vector of center of mass. So where m1, m2 and up to mn are the masses of the particles within the body, and r1 bar, r2 bar, so on and so forth up to rn bar are their position vectors. Then the position vector of center of mass is found like this. Okay, m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar. Okay, and what does it mean by the total mass of the body is supposed to be concentrated at that point? So it means that, okay, so we saw it yesterday. So in denominator here we have total mass of the body, right? Sum of masses of all the particles is total mass. Okay, and if you take that total mass on left hand side, so m times rcm bar will be equal to m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar. And then if you take derivative of this equation with respect to time, what do you get? So you get m1 v1 bar, okay, because derivative of position with respect to time is velocity, plus m2 v2 bar plus so on and so forth up to plus mn vn bar. So this is equal to m multiplied by derivative of position vector of center of mass with respect to time as velocity of center of mass. So it means if you add momentum of all particles of the body, what do you get? You get mass of the body multiplied by the velocity of the center of mass. Okay, so as if the total mass of the body is concentrated at the center of mass. And if we take one more derivative, so we see that, so if we take derivative of this dv by dt, then suppose mass is constant, so derivative of velocity with respect to time will give you acceleration. Okay, so mass times acceleration is the force. Okay, so force acting on first particle plus force acting on second particle plus so on and so forth up to plus force acting on nth particle. So this is the total external force acting on the body. Okay, so if you take one more derivative of this with respect to time, okay, what do you get? dv by dt is acceleration. So mass times acceleration is force. Okay, so this will be the force acting on first particle, force acting on second particle, so on and so forth up to plus force acting on nth particle. So sum of all these forces will be the total external force acting on the body, right? And it is mass of the body multiplied by acceleration of what? Acceleration of the center of mass. Okay, so again it tells us that we can think as if the total mass of the body is concentrated at the center of mass, right? So this is what we saw yesterday. Okay, and then there was an internet issue. Okay, so if external force is zero, what will happen to the acceleration of center of mass? So acceleration of center of mass will be equal to zero, right? So let's suppose we have a bomb, okay, over here, and it explodes into several pieces. Okay, so initially it is at rest, it explodes into several pieces. Okay, so one piece goes like this in this direction, one piece moves in some other direction, one piece moves in this direction, one piece moves in this direction. Okay, so my question is, and let's suppose m1, m2, m3, m4 are the masses of those four pieces. Okay, v1, v2, v3, v4 are their velocities. So what will be the velocity of center of mass? Right, it will be 0. Okay, so center of mass will remain at that location only. Why? Because there is no external force, and since there is no external force, the acceleration of center of mass will be 0. So initially, if it was at rest, it will remain at rest. If it was moving with some velocity, it will keep on moving with that velocity, right? Okay, let's take another example. So let's suppose we throw an object in space. Okay, so the object will move like this, right? And when it is at this location, that object, again you can consider a bomb, it is at this location. It breaks into several pieces. Okay, let's suppose it breaks into three pieces. One piece moves in this direction, okay, the other one moves in this direction, and the third one moves in this direction. Okay, so now the question is, after that point, where will the center of mass go? Okay, so if one piece whose mass is m1, it moves in this direction with velocity v1. Second piece whose mass is m2 moves in this direction with velocity v2. Third piece whose mass is m3, okay, it moves in this direction with velocity v3. In what direction will the center of mass go? Along this path. Okay, along this path, the projectile motion. It will continue the projectile motion. Okay, why? Because let's suppose the object is here and you're throwing it upwards. Okay, like you're throwing it in this direction, making some angle with the horizontal. So the object performs projectile motion, right? So center of mass performs projectile motion. Now the object breaks into some pieces. It's because of the internal force only. So there is no external force acting on the object which is resulting into this breaking. Okay, this breaking is not because of the external force. It's not because of gravitational force or any external force. And therefore, the center of mass will keep on moving in same direction. Okay, so object was under the influence of gravitational force. That means the center of mass, and we can think as if the total mass of the body is concentrated at center of mass. So object was under the influence of gravitational force, means the center of mass was under the influence of gravitational force. So it will keep on moving in same direction, right? Same direction meaning it will keep on following this projectile path. Okay, so is this thing clear? So another example can be taken of a reaction. Okay, so let's suppose we have an element. So let's suppose we have an element X. Okay, so this is an atom. Okay, X is an atom. So this atom was moving in this direction with some velocity. Let's suppose the velocity is v bar. And now all of a sudden what happens? There is an alpha particle gets emitted. Okay, so this atom was moving in this direction, and this atom breaks into what? An alpha particle and some other element. Okay, so alpha particle gets emitted in this direction. Okay, and the element moves in this direction. Okay, so this is a nuclear reaction. This is called as alpha decay. So the alpha particle is small. Okay, it has nucleus of helium. It moves in this direction, and now let's suppose the element becomes Y. Okay, so earlier the element was X, now it has become Y. So this Y keeps on moving in this direction. Okay, moves in this direction. So now question is, in what direction will the center of mass move? So the center of mass of the system. Okay, so I'm sorry, since earlier this atom was moving in this direction, okay, towards right with some velocity v. So there is no force, no external force acting on the center of mass. So center of mass keeps on moving in the same direction. It keeps on moving in the same direction. Okay, with same velocity v bar, right? Then we can take another example. So there is an example in astronomy. Okay, not astrology, astronomy. Okay, binary star system. Okay, what is binary star system? So these are two stars. These are two stars, and they rotate about themselves. I mean, the first star rotates about the second star rotates about the first star. So they rotate like this, okay, about each other and move in space. So if you look at their motion, so if you concentrate on one star, so how will its path look like? Its path will look like this. Okay, its path will look like this. Right. But in what direction will the center of mass move? So in reality, what happens is these two stars, they revolve around the center of mass and the center of mass is moving in a straight line. Okay. So two stars are revolving around the center of mass and that center of mass is just moving in this straight line. Okay. So in the binary star systems, you have two stars of almost same mass, M1 and M2. So they revolve around each other and move in space. Okay. So actually what happens is both of them revolve around the center of mass of the system. Okay. They perform circular motion about the center of mass of the system and their center of mass is moving in a straight line. Okay. So if we think in terms of center of mass, then the motion is simplified. So let us solve some questions on center of mass. So we already solved some questions yesterday. Okay, so let's move on to the next question. Three identical metal balls, each of radius r, are placed touching each other on a horizontal surface such that an equilateral triangle is formed when centers of three balls are joined. The center of mass of the system is located at, okay, line joining centers of any two balls. All right, so let me draw it. So we have three balls like this. Okay. So they are touching each other. Three metal balls, they are identical, touching each other. Each of radius r are placed touching each other on a horizontal surface such that equilateral triangle is formed when centers of three balls are joined. So if you join their centers, what will you get is an equilateral triangle. Okay. Question is, where will be the center of mass? Yes, option A, line joining centers of any two balls. Will it be along this line? It will not be. Center of mass will be here. Okay, you can think of symmetry, right? Center of one of the balls can't be there. Okay, center of one of the balls. So it can't be here, right? Center of mass. Horizontal surface. It cannot be on the horizontal surface because mass is above the horizontal surface, right? So point of intersection of three medians. So this is the answer. Point of intersection of three medians. Okay, so if you draw medians like this, 1 2 3, so they will intersect at this point. Okay, they will intersect at this point, right? So you can see the mass of this system is equally distributed in all directions about this point. Okay, so this will be the center of mass. Okay, clear? All right. So Ravindran already said it's clear. Good. Then this next question. The center of mass of system of particles does not depend on position of particles, relative distances between the particles, masses of particles, and forces acting on particles. So what's the formula? It is m1 r1 bar plus m2 r2 bar plus so on and so forth. Okay, up to plus upon m1 plus m2 plus so on and so forth up to mn. This is the position vector of center of mass. So it depends on masses. It depends on the positions of these masses. Okay, and because it depends on positions, it means that it depends on the relative distance also. Okay, it depends on this, depends on this, depends on this. It does not depend on this thing. Okay, we can find it out from the formula, right? Okay, good. So next question. Two persons of masses 55 kg and 65 kg respectively are at opposite ends of a boat. So you have a boat. These are two people, okay, on opposite ends of boat. The length of the boat is 3 meters. So length of the boat is 3 meters. Good. Okay. And its weight is 100 kg. Weight of this boat is 100 kg. Okay. The 55 kg man walks up to the 65 kg man. So suppose this is 55 kg man. He walks up to 65 kg man and sits with him. If the boat is in still water, the center of mass of the system shifts back. Option C, right? So option C, because there is no external force. Okay, whatever the masses do internally, right? There won't be any acceleration of center of mass. Okay, it won't change the velocity of center of mass. So if initially the velocity was 0, then again the velocity will remain 0. If it was at rest, the center of mass, then the center of mass will remain at rest, right? So option C is the answer. Very good, Ravindran. Two particles which are initially at rest move towards each other under the action of their internal attraction. Okay, if their speeds are v and 2v at any instant, then the speed of center of mass of the system will be, again the answer must be 0, right? They are moving by the action of internal force. So it can be, let's suppose these are two particles initially at rest. Okay, this is at point A, this one is at point B, and there is gravitational attraction between them, right? There is gravitational attraction between them. So it is the mutual attraction. Okay, it's the internal force for this system, and therefore since there is no external force acting on the system, if we think about both the particles, both the bodies, there is no external force, and that's why the center of mass, because initially those particles or those bodies were at rest, so the center of mass was at rest. So because there is no external force, the center of mass will remain at rest. So option B is the answer. The next one, three bodies having masses 5 kg, 4 kg, 2 kg is moving at a speed of 5 meters per second, 4 meters per second, and 2 meters per second respectively along x-axis. The magnitude of velocity of center of mass is. So again, this is simple. So we saw that velocity of center of mass times the total mass. Okay, m times velocity of center of mass is m1 v1 plus m2 v2 plus m3 v3, and you can move that m on this side, so it is m1 plus m2 plus m3 is the m. Okay, so we just have to put the values. So 5 kg times 5 meters per second plus 4 kg times 4 meters per second plus 2 kg times 2 meters per second, and in denominator we have 5 plus 4 plus 2. Okay, so it is 25 plus 16 plus 4. So this is 20. 20 plus 25 is 45. 45 divided by 11. Okay, 45 divided by 11. So it is 1 point something. I'm sorry. It is 4 meters per second. Yeah, sorry. All right. So a block of mass m slides with velocity v along a frictionless level surface towards a block of mass 4m initially at rest. The velocity of center of mass is. So this one is simple, right? So velocity of center of mass is equal to block of mass m moves with velocity v along a frictionless surface towards a block of mass 4m whose velocity is 0. Okay, so m1 v1 plus m2 v2 divided by m1 plus m2, which is m plus 4m. So in numerator we have m times v, denominator 5m. So mm gets cancelled, v divided by 5 is the answer, right? Okay, v divided by 5 is the answer. Simple. Okay, next question. Two bodies of different masses of 2 kg and 4 kg moving with velocities 2 meters per second and 10 meters per second towards each other due to mutual gravitational attraction. What is the velocity of their center of mass? Again, they are moving due to the mutual gravitational attraction. This thing is important. Okay, they are moving due to the mutual gravitational attraction. It's not the external force. So initially they would be at rest. Okay, so no external force is acting, and this velocity is gained by mutual gravitational attraction only. And that means since external force is 0, earlier the center of mass was 0. Center of mass was at rest. That means its velocity was 0. So it will remain 0. Okay, and that's why the answer is 0. Alright, so let's see this question. A man of 50 kg mass is standing in a gravity-free space at a height of 10 meters above the floor. Okay, there is gravity-free space. So there is some floor, hypothetical floor, this one, and there is no gravity on this floor. And the man is standing in space above the floor, 10 meters above the floor. Okay, so this is that man. He throws a stone of 0.5 kg mass downwards with speed of 2 meters per second. When the stone reaches the floor, the distance of the man above the floor will be. This is the question. So see, so the man is holding a stone. He throws that stone downwards. Okay. So what will happen? So he can only throw the stone downwards by applying some force, right? So equal and opposite force will be applied by the stone on the man also. Okay. Initially both of them were at rest. So what can you say? How much would be the velocity of man if stone moves downwards with velocity of 2 meters per second? 2 meters per second. How much would be velocity of man? So we can say initial velocity was 0, m1 u1 plus m2 u2 is equal to 0. So m1 v1, or let's call man and stone. Okay, so mass of stone times velocity of stone. plus mass of man, let's call it m only, times his velocity is equal to 0, because initially the man was holding the stone and he is in gravity free space, so he is floating at that point. Okay, so velocity was 0, so final velocity, sorry, total momentum was 0. Okay, and therefore we can find out velocity of man. So v will be equal to what? It will be in opposite direction, right? So let's call this negative. Okay, minus 2 meters per second, and then let's substitute the values. So this is 0, this is mass of stone is 0.5, velocity of stone, because it's moving downwards, I'm calling it minus 2 meters per second, right? Plus mass of man is 50, velocity of man is what we have to find out. So move this on left hand side, so it will be 0.5 into 2, that is 1. Okay, so velocity of man is equal to what? 1 by 50 meters per second. So now the stone reaches the ground. So stone is 10 meters above. In how much time will it reach the ground? In 5 seconds, right? Because its speed is 2 meters per second and this distance is 10 meters. So in 5 seconds it will reach the ground. Now the man was here earlier. Okay, so with this much velocity, how much distance will he cover? How much distance will he move upwards? So it will be distance covered by man. Okay, so distance covered by man, suppose s, it's equal to velocity of man multiplied by time. So that is 1 by 50 multiplied by time is 5 seconds. Okay, so 5 divided by 50 is 0.1. So he was already at 10 meters. Now he moves zero point 0.1 meters upwards. So that means at what height will the man be? 10.1 meters, right? He will be at the height of 10.1 meters. Principle of moments of mass, moments of masses, we can say. Okay, what is this? Principle of moments of masses. So we saw that the position vector of center of mass is given by what? m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar divided by sum of masses of all particles of the body. Okay, m1 plus m2 plus so on and so forth up to mn, which can be written as what? Total mass of the body. Okay, and now let's suppose this is the body. So what is the moment of any mass? So moment of mass is mass multiplied by its position vector from the origin. Okay, moment of mass is what? Moment of mass, what does it mean by moment of mass? It is a mass multiplied by its position vector, right? So what is moment of this mass m1? It's m1 r1 bar. Okay, moment of mass m2 is m2 r2 bar. Okay, so now let's suppose we take the origin at center of mass. Okay, so let's suppose we take the origin at the center of mass. So let's suppose this is or xyz coordinate system, xyz coordinate system. This is x, this is y, this is z axis. So this is the center of mass of this body. So what will be the position vector of this center of mass? It's 0, right? It's 0 bar. Okay, so position vector So suppose the origin is at center of mass. Origin of the system, origin of this coordinate system, sorry, coordinate system is the center of mass. Okay, so what will be its position vector? It's 0, right? 0 bar you can say. Okay, so RCM, the position vector of center of mass, is 0 bar, and therefore what will be sum of moments of masses of all particles, and therefore we can say the sum of moments of masses of all particles. So now you are calculating moments of masses with respect to what? You calculate them with respect to some origin, and now you are considering what? The origin is the center of mass. Okay, so what will be sum of moments of masses? So since the position vector of center of mass is 0, 0 bar you can say, so sum of moments will be equal to 0. Okay, so it is m1 r1 bar plus m2 r2 bar plus so on and so forth up to plus mn rn bar, and this will be equal to 0. Okay, so this is simple principle, and we can write this in symbolic form. Summation of I goes from 1 to n moments, sorry, mi ri bar is equal to 0. So this is the principle of moments, moment of masses. Is it clear? We are going to use this concept in the topic called parallel access theorem on moment of inertia, that we'll see in the same chapter. Okay, so till now we talked about till now we talked about the center of mass of discrete particles, right? So now let's see how to find out the center of mass of continuous object. Continuous objects or continuous bodies you can say. Okay, so I drew a body like this. Okay, and I said it is made up of n number of particles. But when I say that, it is always some approximation, right? It's always some approximation. Okay, so actually when we have a body like this, a continuous body, we cannot say that it's made up of n number of particles. We have to, so when we say it is made up of particles, then it means that we are considering some discontinuities, okay, where the mass is continuous. So what is the best strategy to find out the center of mass of this kind of objects? So what we can do is we can break this object into several pieces, very small pieces. Okay, and now to consider any small piece. Let's suppose you consider this much. Okay, so this one small piece. So mass of this piece is suppose dm. Okay, mass of this piece is suppose dm. Now if the masses, if the body is linear, then you can consider linear mass distribution. If it's an area, then you can consider areal mass distribution. If it's a volume, then what we can do is we can say that density of this body is the mass upon volume. Okay, so let's suppose dV is the volume of this piece. Okay, so how much will be its mass? So now if you move this volume on left hand side, you can write mass of the body is volume multiplied by density. Okay, So this is density, right? So density is mass upon volume. So mass is density multiplied by volume. So the mass of this piece, let's call it dm. So dm will be equal to what? Dm is density multiplied by small volume dv. Okay. So now how to find out the center of mass? So consider some coordinate system. So let's suppose this is two-dimensional object only. So consider a coordinate system like this, x and y coordinates. Okay. So some this piece will have some position vector. Let's suppose the position vector is r bar. Okay. So you take one mass, okay, dm, and you find its position vector. Suppose it is r bar. Okay. So you do it for all such small pieces on the body and add it up. So there will be n pieces. Let's suppose I goes from 1 to n. Okay. And you find dmi multiplied by ri bar. Okay. Sum of that over this total entire body. So what will you get? So this is the moment of these masses. And if you divide it by the mass of the body, what will you get? You will get position vector of the center of mass, right? You will get the position vector of center of mass. Okay. And if n tends to infinity, what will happen? So we have seen, if we have a summation where n tends to infinity, then that summation becomes what? An integration. Okay. Then the continuous addition becomes what? An integration. So the center of mass for continuous bodies is given by what? Integral of dm into r bar divided by m. Okay, this is how we can find out the position vector of center of mass for continuous mass distribution. Okay, so of course this is an abstract concept. So once we see an example, it will get clear. So let's suppose we have very thin rod. Okay, this is very thin rod. It's kept like this. The length of this rod is L. L is the length of this rod. Okay, and uh, let's suppose this end of the rod is at the origin. Okay, the end is at the origin. So of course the right end will be at distance L from the origin. Okay, and thickness of this rod is minimal. So what we can do here, so let's suppose I want to find out center of mass of this rod. So now symmetry will tell you that center of mass will be here, right, at x equal to L by 2. Okay, so from origin just draw a straight line, then on that line at distance L by 2 will be the center of mass. Okay, so that's what we can find out. Okay, so this is a continuous body. What we can consider is, we can consider the linear mass distribution. So let's suppose mu is the mass per unit length of this body. So mass is m, length is L, right? So mass per unit length is mu. Okay, so then let's consider a small segment, the small segment, and length of this segment is suppose dl. Okay, so how much will be the mass? Mass is suppose dm. Okay, so what will be dm? So dm can be written as, so see, mu is the linear mass density. Okay, what is mu? It is mass per unit length. It is known as linear mass density. Okay, so it is mass per unit length. Therefore, if I consider that there is uniform mass distribution, then how can I write dm? So I can say that mu is equal to this mass dm divided by length dl. That means if I consider any length of this body, then mass of that segment divided by length of the segment will give me what? Same mu, because mass is uniformly distributed. Got it? It means that if you take half length, okay, if you consider half length, the mass of that half length will be how much? It will be half. If you consider one-fourth length, the mass will be one-fourth. Okay, so mass is uniformly distributed, right? So therefore, dm can be written as what? Dm can be written as mu times dl. Okay, and then how to find out the center of mass? So now there will be only one coordinate to center of mass, x coordinate of center of mass. It is equal to integral of x dm. Okay, integral of x dm from where to where? So it will be from 0 to L, right? Divided by mass m. Instead of x, I will call it L. So let's suppose the x position. Okay, let's suppose the x position of this length is L. Okay, so I can say it is integral of L dm. Okay, integral of L dm divided by m. Right? Yes, no? All right. So now you can put dm is equal to what? Mu times dl. Okay, so here you have two variables. One is length meaning the x coordinate, and the other is its mass. So we have to convert it from two variables to one variable, because we want to integrate it over this body. So therefore we write dm equals to mu times dl. So it is mu times dl. Okay, this is dm multiplied by l. Okay, divided by m. So now, because we have only one variable, so we can put limits of integration. So L will change from 0 to capital L, right? Then we can take mu out. So mu upon m we have. Okay, so integral from 0 to capital L of L dl is what? L square divided by 2, right? So mu upon m multiplied by, we have L square upon 2. Okay, this is small l, and lower limit is 0, upper limit is capital L. So it will be capital L square divided by 2 minus 0, or we can say it's capital L square divided by 2 only. Okay, and then we can write mu equals to what? Mu is m upon capital L. So we have m upon capital L, that's mu, divided by this mass multiplied by L square divided by 2. So this m gets cancelled, the square gets cancelled with L. So we are left with L by 2. So we have x coordinate of the center of mass of this system, this rod, is equal to what? It is L by 2. Okay, so very straightforward derivation. Got it? Yes, no? Okay, so I have semicircular ring like this. Okay, this is semicircular ring, right? So mass is above the x-axis only. Below the x-axis there is no mass. That means the center of mass will be little bit above the x-axis. Okay, so its x coordinate will be equal to 0. Y coordinate is what we have to find out. Okay, so we have semi-circular ring. Let's suppose it's very thin. Okay, so now it will have some length, right? So just like the previous problem, we can consider that it has got linear mass density. Let's suppose mu, it is mass upon length. Okay, it's the linear mass density. So let's consider a small mass. Let's consider a small length segment. So I will consider this small length segment. Okay, so now this length segment is very narrow. Let's suppose it's very small. Okay, so it will have some x coordinate, some y coordinate. Okay, it will have some x coordinate and some y coordinate, right? So that we can find out. So this is suppose the x coordinate of this length segment and this is the y coordinate, right? So this is r. Okay, this is r and this angle is theta. So we can say what is x and y. Okay, so let's suppose that this length segment is dr. Okay, let's consider the length segment dr. So in terms of mu, we can write it as mu equals to what? What will be mass of that segment? So let's suppose mu, sorry, it has mass of the length segment is equal to dm. So this dm can be written as what? Dm is mass of this segment. It can be written as what? The linear mass density multiplied by its length, right? So dm is equal to what? The linear mass density mu multiplied by its length dr. Okay, and now I want to find out the x coordinate and y coordinate. So if we think about this triangle, so how much will be this distance? It will be r cos theta. And how much will be this distance or this distance? It will be r sin theta, right? So x is its x coordinate. Okay, so for the length element, we can say x is equal to r cos theta and y is equal to what? R sin theta. Okay, so now what we can do is we can find out the x coordinate of center of mass. What will be x coordinate of center of mass? So if we consider such small mass elements, okay, small length elements, and we find out the x coordinate of all of them, and if we integrate over what? Over this ring and divide it by mass of the ring. Okay, so if we take x times dm, okay, where x is the x coordinate of mass dm, and we integrate it over this body and we divide that by mass of the body, we'll get x coordinate of center of mass. Similarly, to find y coordinate of center of mass, we have to find y coordinate of mass dm and we have to integrate y times dm over the body and divide it by m. So this way we can find out the y coordinate. Now see, I can write, let's find out x coordinate first. So xcm is equal to integral of x dm, and how much is x for this mass? It is r cos theta, right? It is r multiplied by cos of this angle theta. Okay, so it is r cos theta. And now what is dm? So I have substituted x. What is dm? Dm is mu multiplied by, mu is mass per unit length, mu multiplied by this length. Okay, this length of this segment. So it is mu dr, and in denominator we have capital M. So now you can see here we have two variables. Okay, so dr is a variable, minimum value of dr is 0, and at max how much length element can we have? The total length, right? Total length, how much would be total length? How much is value of L? If r is the radius of semicircular ring, then pi times r will be the length. Okay, the semi circumference you can say. Circumference is 2 pi r, but we have half of that only. Okay, so pi times r. Okay, length is equal to pi times r. So minimum is 0, maximum we can have pi times r. So that's one variable. And theta is another variable. Theta is another variable, right? So minimum value of theta is 0. How much is the maximum value from here to here? It's 180 degrees, or pi you can say. So either you have to convert theta in terms of the dr, or you have to convert dr in terms of theta, right? So we cannot have two variables in an integration. So what we'll do is we'll convert the dr in terms of theta. So dr is length of this arc. Okay, it is length of the arc. See, let's suppose this much angle, this small angle is d theta, and this radius is of course r. Okay, so small angle subtended by this arc of length dr at the center is suppose d theta. Okay, this radius is r. So we know what is arc upon radius. What is arc upon radius? It's angle d theta. Okay, what is this angle d theta? It is arc upon radius dr divided by r, and therefore we get dr equals to what? It is r multiplied by d theta, and we can substitute that over here. Okay, so now mu is constant, we can move it outside. So what we get? X coordinate of center of mass is integral of r cos theta times mu multiplied by dr, which is r d theta divided by m. So now we have only one variable. Theta is only one variable that we have. Got it? Yes, no? So then what we can do is we can move this r and mu also outside. So what do you get? X coordinate of center of mass is equal to mu r square upon m, and then you have integral of cos theta d theta. Okay, so simple. And the angle will change from 0 to pi. What is integral of cos theta? Sin theta. Right, so it is equal to mu r square divided by m sin theta, and the angle changes from 0 to pi. So that is mu r square divided by m. So let's put the upper limit and the lower limit. So upper limit is pi, lower limit is theta. So it is sine of pi minus sine of 0. Right? What is sine pi? Sine 180 is 0. Sine 0 is also 0. So it's 0 minus 0. Right? So x coordinate is equal to what? 0. Okay? Got it? Yes, no? Yes, Ravindran. Okay. So x coordinate is 0. Okay. So these are 9 coordinates. So we have to find. So now let's find out y coordinate. So y coordinate of the center of mass is 1 upon m multiplied by integral of I dm. That is 1 upon m. Similarly, we can write the integral of y dm. Y is theta and dm is mu dr. Sorry, it is r sin theta. Okay. So y coordinate is r sin theta multiplied by dm is mu times dr. Again, we can write dr is equal to what? So dr is equal to r multiplied by theta. So let's write that. So we have 1 upon m multiplied by r into sin theta multiplied by mu multiplied by r multiplied d theta in just take basis mu r square we take out. It is mu r square divided by m multiplied by integral of sin theta d theta from 0 to pi. Okay. So what is integral of sin theta? What is integral of sin theta? It's minus cos theta. Okay. It is minus cos theta. Right? You will have mu r square divided by m. So this is integral of sin theta is minus cos theta. So it is 0 or it is pi. Okay. So what do you get? You substitute that. So it's breaking. Okay. So we just have to perform this integral. Okay. To find out y coordinate. Okay. We just have to perform integral. Okay. So that I will just do. You see that, and then we'll stop. Fine. So I will show that. I will perform the integral. I will show that. Okay. Just okay. It is integral of minus cos theta. Sorry. The integral of sin theta is minus cos theta. Hopefully it's not breaking now. Yeah. So let's do it quickly. So I coordinate of center of mass will be what? Mu r square divided by m multiplied by. Now you can take this minus in common. You can it is minus cos of pi minus cos 0 minus plus plus cos 0 and you substitute upper and lower limit. So upper limit is pi, lower limit is 0. It is minus of cos pi minus of minus cos 0. So you will get the same. Okay, yes, no. All right. So just substitute that. So what is cos pi? Cos pi is minus 1. Okay. So minus of minus 1 is 1. Okay. And cos 0 is also 1. So it is 1 plus 1, 2. Right? So it is mu multiplied r square times 2 divided by n. And what mu? Substitute. What mu? So mu is m divided by pi r. Okay, mu is m divided by pi r. So let's substitute that. Substitute that mu is m upon pi times r. You have r square upon m multiplied by 2. So something gets cancelled out. You can see M and N get cancelled out. R square get cancelled out with R. Okay, and what is left is y coordinate of center of mass is equal to twice R divided by pi. So this is the y coordinate of center of mass of a semicircular ring. Okay, so let it appear on your screen and tell me if you have a question.